In our previous lecture, we developed a nice recursive relationship that described the evolution of our weight vector as we applied our gradient descent algorithm. We did this by defining a delta weight vector, we called delta W, that was equal to the current weight vector minus the optimal weight vector. By so doing, the relationship became very straightforward and simple, except for the fact that we're dealing with raising a matrix to a power, that's I minus mu Ry. Well, it's hard perhaps to have intuition as to how that's going to proceed. Obviously we have an engine to apply the math, but we would like to really know what's going on. So in order to get a little more insight, we're going to take advantage of the fact that Ry is symmetric and it's square, and so we can use the spectral matrix factorization that we introduced earlier in the course. In this case, Q is a unitary matrix, that is Q times Q transpose is equal to I, or in other words, Q transpose is the inverse of Q. And Q is made up of columns that are eigenvectors of the matrix Ry that are normalized to make them unit norm. And the lambda is a diagonal matrix that contains the eigenvalues of Ry. Now we can use this relationship, plugging that into our recursive equation above, and since we can also express I as Q transpose, we can factor the Q and the Q transpose out of this equation, and we're left with something in here that's a diagonal matrix. And now we're going to go one step further. We're going to multiply both sides of this equation on the left by Q transpose. At this point, we can see that every time W appears in this equation, or delta W, it appears with a Q transpose in front of it. So we'll do a simple substitution, and we'll just say a new matrix, or vector, rather V I is equal to Q transpose delta Wi. That enables us to rewrite the equation one more time as Vi plus 1 is equal to, now we have this nice diagonal matrix, times Vi. Okay, Vi is now a column vector, and since we have a diagonal matrix multiplying this column vector, that means that the elements of Vi don't affect each other. And so we can now write this as n or p or whatever our dimension is, individual equations that we can capture in a matrix this way, where Vi plus 1, and I'm going to change notation here just to keep things kind of clear. We'll put the I plus 1 in parentheses up above, so we can put the vector element right in here. That would be 2 I plus 1 all the way up to V, let's say P I plus 1. And that's just equal to, now, 1 minus mu lambda 1 times V1 at iteration I. And this continues 1 minus mu lambda 2 V2 at iteration I, and so on and so forth. So these equations are now decoupled, and we can just express this generally as V k I is equal to 1 minus mu lambda k, and we can raise this to the I power vk I minus 1. No, I misspoke. Vk of 0, our initial guess. So now we have each and every component of this we want to go to 0. So as I increases, we should have 1 minus mu lambda k to the I should go to 0. To accomplish this, we just simply need to guarantee that 1 minus mu lambda k is less than 1 in magnitude for every k, or every lambda k. Let's say for every k. Okay. As before, this is what we saw when we looked at the one-dimensional case, and now we have p one-dimensional cases. So everything's the same, except that we're going to have to apply this constraint on everything. And so we're going to want mu to be greater than 0, of course, and less than 2 over lambda k for all of the k's, to ensure that everything, all modes, if you will, converge. Well, in order to ensure this, we the operative or the most constraining equation is going to be that with lambda max. And so that implies that mu must be less than 2 over lambda max, so that all modes decay to 0. With the one-dimensional case, we were able to come up with a method of jumping to the correct solution in a single step. That was mu was equal to 1 over, in that case it was ry, which was a scalar. In this case, we get the same type of behavior. That is, if mu is equal to 1 over lambda max, then we have a perfect solution in one step, but it's only for that mode. So only one mode, or one of those equations, will decay to 0 in one step. The others are going to be more slow. Okay, now we have the tools to look at how this entire system will converge. If we go back to our error at iteration I, we're going to have emin plus, and this is from what we had before, our delta weights. Let's see, using our new notation at time I, ry, and the same delta weights like so. Well, using the factorization we had introduced above, this now becomes vi, actually, sorry about the switching notation in the middle here, but we're going to put the i's back in the subscripts because we don't have to deal with the difficulty of having matrix elements and iteration numbers. So transpose vi. So we can now write this out. This is going to be E min plus this sum here. Okay, so let's unpack briefly what's going on here. Our VI transpose lambda VI is going to give us a quadratic term. Each of these VI's is a function of our 1 minus mu lambda k. So when we multiply this out, we're going to get a exponent of 2i up there. And that relates everything back to v naught, as we showed up here in the upper right of your screen right now. The lambda I comes out from our capital lambda, our diagonal matrix, and the V transpose lambda V performs the summation. So this is just our VI transpose lambda VI. And what does this tell us? This tells us that the total error is the error contributed by each mode, as we've been calling it. Some of these modes are going to decay very, very quickly. If 1 minus mu lambda k is very small, then that value will go to 0 quickly. If, on the other hand, it's close to 1, that value goes to 0 very slowly. And so we end up getting behavior that looks like this. If we were to plot our error, the first mode is going to drop rather quickly. The next mode will be slower, and so on and so forth, so that our error is going to decrease. This is approximate here, like that. There will be a time when it's decreasing very quickly. When that mode disappears, it will then decrease a little more slowly. When that mode finally gets really small, it decreases more slowly yet, so you get this long tail. In an ideal world, all of the eigenvalues of Ry are going to be the same. And if they're all the same, then everything will decay at the same rate. And we can choose our mu so that it's the fastest rate possible. Ideally, we would choose mu to be 1 over this lambda, and so everything would jump to 0 extremely quickly. In practice, that can't usually happen, but we can choose something so that it decays very quickly. However, if the eigenvalues of Ry are widely spread, there is no optimal value. And so while we may choose mu so that one mode decays quickly, necessarily the other modes will be much more slow.